we'll be hearing from Kavitha Prasad. She's the VP of System Solutions at a startup called SiMa.ai. Kavitha is the VP of their Systems Solutions and previously worked at Intel in a variety of roles in embedded system solutions. So welcome, Kavitha. You can go ahead and share your screen, and we'll get started with your presentation.
Sounds good. Let me know when you can see the screen, Mike.
Yeah, that looks good.
Sounds good. Thanks a lot to all of you for attending this session on SiMa.ai, and thanks to Linley for giving us an opportunity to host this session. Like Mike mentioned, my name is Kavitha. I manage system applications and business development at SiMa.ai. Today, what we'll be walking through is the machine learning SDK that we have developed to target our edge AI MLSoC that we are developing in-house. Most of us actually think that machine learning is more of a hardware problem, but from SiMa.ai perspective, from the beginning, we thought it was as much a software problem as it is a hardware problem. Even with the best optimized hardware architecture, if we don't have the robust software stack to go with it, we believe that one, the solution is not going to be scalable, and two, you will not be able to extract the best performance out of the hardware. So with that in mind, from day one, our focus at SiMa has been how the software hardware co-design so that you get the best performance out of a machine learning accelerator. And today we'll walk you through the software SDK that we have developed for our machine learning accelerator, and also focus on how easy it is to use to deploy the machine learning inference workloads on our SDK. Sorry. So for those of you who attended the Linley conference in spring, we introduced our MLSoC in that conference. What we'll be focusing today on is the machine learning accelerator, which is the 50 TOPS at 5 watts peak performance, effectively 10 TOPS per watt peak performance, and how the SDK we are developing targets this machine learning accelerator. At a very high level, when we went around building our SDK, the key focus we had in mind is what is the customer experience going to be? One, how easy is it for the customer to use? And two, how easy is it to deploy? With that in mind, what we did was we went ahead with the industry standard TVM framework as the basis for our SDK. And we received a lot of feedback from our customers too, and that's how we decided TVM is the right way to go. The whole software stack that we are building is capable of running on simulators. The workflow can run on simulators, or it can run on emulator, or when the hardware is available, you can easily target it to the silicon too. But from a customer usage perspective, they are agnostic. All they need to do is specify the target and the workflow remains the same. And the SDK is also integrated for ease of use into an IDE, industry standard IDE, which is complete with the visualization, debugging, and profiling capabilities. So through this SDK, we worked with actually 20 plus customers, and we have ran 40 plus benchmarks out of this SDK flow that we have today. And this is a snapshot of one of the KPIs, which is TOPS per watt. But by running these workloads, we are also able to give other KPIs like frames per second per watt, utilization, memory analysis, etc. All those can be also produced. The key thing when showing these benchmarks, few of the things to observe are these benchmarks and these performance metrics were right out of our tool chain. There was no hand tweaking that was done to provide these metrics. Number two, these benchmarks were run across multiple frameworks. Some of them are Onyx, some of them are PyTorch, TensorFlow, TF-Lite, or even MXNet. So we are framework agnostic. You can give in any frameworks. Our SDK will be able to handle it. Three, these benchmarks are across variety of workloads. Some of them are object detection, object classification, semantic segmentation. We have run YOLO, we have run KittySeg, we have run ResNet, MobileNet, etc. through this SDK, and we are able to get the performance right out of the toolchain. And the other key important thing is also across all these workloads, our frame sizes do vary. Some of them are 24 by 24 by 1, all the way up to 4K or ultra or HD size image input frames. We are able to handle it through our software stack. So we will walk through how to use this software stack for any application in the next few slides. Let's take a simple smart vision application. You have cameras, you have pre-processing, you capture the data frames, and then you do an object detection recognition, tracking, and then some post-processing. This is any typical computer vision application available out there. For today's conversation, we will be focusing on MLA, the object detection and recognition through our MLA. And in the breakout session today, we also have a demo of this. So please do attend, and we will walk through how the demonstration of our entire SDK stack for this particular object detection and recognition workload. So now looking at our SDK stack from a customer perspective or from a developer perspective, first step is you will have your application. You provide that as input into our API or into our SDK through the simple API that is provided below. All you need is to point a pointer to the, in this particular example, we are showing a TensorFlow file, but it could be anything. It could be PyTorch, MXNet. We are agnostic to any of it. Just give it as an input, specify the inputs and specify the outputs. And we leverage the TVM framework for the conversion and the graph optimization. So when that API gets run, for example, if your network has more inputs, multiple inputs and multiple outputs, it's very simple to specify in this API. Just specify the inputs, specify the outputs, and it's done. And when you go through this particular step of the first step of the SDK, and when you run that API, what happens is we are running hardware agnostic optimizations take place during this step. It could be removal of unused functions, fusing of operations, removal of dead code. So basically, we take the input graph, we do hardware agnostic optimizations, and you get an intermediate representation. Now you can continue to go through the flow and run continue to run the inferencing, or you can save the network or the intermediate representation of the network and reload it at a later point of time and go through the flow. So the next time you want to reuse the network, you don't have to go through the same graph optimizations again, because it's already there. So in this case, now if we decide to save the network after the graph optimizations, just use the API and we save the network. Two files are generated and stored. One is the constants file, which is the NPZ file, and the other is the network topology, which is the JSON file. And then if you want to reload, if you want to load the network, again, there's a simple API where you load the network back. And the key thing is also that like I mentioned, we want to stay as much industry standard as possible. Say you have a network that you went through the optimizations and you want to visualize it. You can use the industry standard tool like Netron to port over the JSON file and see what optimization happened and what was the original graph and how does it look after it went through our optimization phase. Having said that, we also are providing Eclipse Thea-based integrated development environment for the customers to use, where they can visualize the entire graph optimization as it goes through our SDK flow. And also there are capabilities to look at the runtime views. What is the memory looking like? What is the compute scheduling looking like? What is the what is the utilization of the cores? All aspects of the runtime and also the graphical views can be visualized in this environment. It's a complete profiling, debug, it's a profiler, debugger, and a visualizer all in one. So now that we have gone through the hardware agnostic optimization, the next step is to quantize the graph. Because our machine learning accelerator runs on int8 operations, we are providing the APIs for the customer to take that FP32 network and go through the quantization. All the customer needs to do is specify the API and specify the type of quantization they want to perform. And from our MLA perspective, we support per tensor quantization, per channel quantization, symmetric and asymmetric quantization. Any form of linear quantization is what we support. Say the customer does not want to quantize it through our flows. They have run quantization aware training and they already have a pre-quantized model. That's fine. At that point, the quantization pass is just going to be bypassed and we will use what the scaling factors, what the 0 points, whatever the customer has, and we'll use that and map it onto our accelerator. But in the case they want to go through our quantization flow, all they need to do is provide the calibration data set. How many times do they want to run this? How many samples do they want to run this? You can run the FP32 inference on the model and collect statistics, calibrate and quantize. You can rerun it and figure out what the quantization, what is the accuracy now after quantization, and we output a quantized graph. So one key thing that happens when you use the SiMa.ai quantization mechanism is that it's optimized for our machine learning accelerator. So we'll get a little bit better performance if, when compared to the pre-quantized networks, because it's quantized for keeping our hardware in mind. So after the quantization is done, it's as simple as running the network. So you run the inference on the SDK. We can target a simulator backend, or we can target an emulation backend, or when the hardware is available, the same flow can target the hardware. To run the network, there is a simple API. All you need to do is use this API and provide the validation data set, and then it just runs and provides the metrics. And then you can post-process the output to generate all the KPIs, all the interested KPIs that the developer is interested in. So what happens during this phase when you enable this API? This is where the hardware dependent optimizations happen. This is where the memory scheduling and the compute scheduling for our MLA takes place. So this is very much dependent on our architecture, and we try to squeeze out the best performance for our architecture. And we will show how this whole SDK runs in the breakout session in the demo that we'll be hosting. But that's pretty much it. You got the network, any framework, run it through the graph or the hardware agnostic optimizations, quantize it, run it through the hardware dependent optimizations, and then you can choose the target of you want to run it on a simulator or an emulator. And when we have our product in the early 2021, you can target it to the hardware as well. But from a customer perspective, they are agnostic. The flow remains the same irrespective of the target they are targeting their inference to run on. So like I mentioned, we have a lot of simulations. We have 40 plus benchmarks running on simulation, and we have quite a few that we have enabled on emulation too. And we are extremely happy with the correlation we are seeing, initial correlation we are seeing between the simulation and emulation. And also we know where the deltas are, and our compiler is still under active development, and we have identified a lot of optimizations that can be done. And the team is currently actively working on that right now as we speak. So in summary, the key focus for us when we developed our SDK is, like I mentioned, ease of use and how easy is it to deploy. So with that in mind, we went with TVM as the base framework for us. We have enabled 40 plus benchmarks working with 25 plus customers across multiple frameworks, multiple input sizes, quantized, not quantized, all kinds of different scenarios, and ran it through our SDK. And benchmarks also include object detection, object classification, and semantic segmentation. And like I mentioned, we do leverage industry standard practices when it comes to even the compiler or even the IDE for that matter. We are going with Eclipse here. We have enabled this SDK with few customers. They have it running in-house, but we are targeting a public release sometime early next year for general public use. That's pretty much what we wanted to cover today.
Thank you, Kavitha.
Thanks a lot, Mike.
Great. So yeah, we'll go to audience Q&A. Please go ahead and enter your questions into the Q&A box. So it's great that you're developing the software, and it seems like concurrently with the chip. A lot of startups stumble on not having the software ready in time. But what is your schedule? You said Q1 or early next year for the chip. Where are you at? Have you taped it out?
Yeah, we do plan to tape it out early next year, but we do plan to have the software available in the hands of the customer even before we tape it out with few selected customers. So our story is going to be a software first story. We will have the software that customers can work with, and we tape out the chip, and when the chip comes back, the same flows, the development just target the hardware and you'll be done. But yes, to your point, we plan to tape out early next year.
So when you talk about the TOPS per watt, it's based on your simulations?
Yes, and we have enabled some of them on emulations too, like I mentioned, and there is a pretty tight correlation between emulation and simulations. But the chart you did see was from the simulations.
Got it. And so for that chip architecture, can you say then you had a computer vision unit as well as your own mosaic MLA tile? Could you say is the computer vision core, is that your own design, or is that something that you're licensing? Could you say what that is?
We are licensing that one, Mike. We are licensing it from Synopsys. So we wanted to leverage as much as possible from the industry that's available and focus on what our value add to this whole system is, which is our memory machine learning accelerator. So the CV comes from Synopsys. It's a EV74 core from Synopsys.
Okay, so then you talk about the programming for your core. What is the software flow? I mean, you're running two separate neural networks. How do the two cores integrate together in their operations?
So if you are running two separate neural networks, it's just a question of specifying two separate networks into the input. And when you run it, you give those as a combined input into the runtime when you're running the network. What happens is the scheduling of how they run together, either concurrent or cascaded, as long as we meet the customer requirements, it's agnostic to the customers. As long as we are meeting the specified requirements from a customer perspective, our compiler takes care of it in the background. So you can run multiple networks, you can specify it to the API, and it will take care of it. Okay.
And then is the CPU, is that a Cortex-M or a Cortex-A?
It's a Cortex-A.
Okay, so let's say some of the questions we have from the audience. We talked about when you plan to tape out. Question from another attendee is do you have any measurements of latency or frames per second for any of the benchmarks that you showed on the power efficiency chart?
Yes, we do. We do have, it's a very good question. Like I mentioned, TOPS per watt is just one metric that we presented. We do have inferences per second or frames per second, frames per second per watt, memory utilization. We have a whole bunch of KPIs that, if customers are interested, and as they run it through the SDK, those do automatically get published, or they can, when you post-process it, those are the KPIs that come out of the tool chain. So yes, we do have inferences per second as one of the metrics.
Okay. In your simulations, I don't recall if you showed this on your block diagram, how much memory do you have on the chip, and were you taking into account DRAM accesses in the simulations?
Yes, we do take, so we have around 20 megabytes of on-chip SRAM, and we have LPDDR4 also. So it's the whole memory management between the hardware, between the on-chip memory and the off-chip memory is taken care of by the compiler. And when we show the simulations, that memory latency is accounted for. And the key thing that our compiler does is it hides the memory accesses behind the compute, and that's one of the key innovations that we have done, and that's where we get the performance from. But yes, when you run the SDK, we do have a visual. You see the memory and compute utilization and what's exactly happening in the pipeline as one of the visualization tools, and the customer can see whether the workload they ran is compute bound or memory bound and figure out what to do about it. But yes, memory is part of our simulations.
Okay, and what simulators are you supporting?
So we have an inbuilt in-house simulator, we have an architectural simulator, we have an instruction-based simulator, and also, like I mentioned, we do support emulator too.
Okay, Poulin, could you go ahead and just turn your camera off for now?
Okay, we'll do that.
And mute your microphone as well.
Yes.
Up next. Okay, great. Then about the quantization flow, there's a question about how aggressive it is. You're just going from floating point to int 8, is that right?
Correct.
Right, okay. And so when you re-quantize a network, is there any retraining required?
So what we do is we use the calibration data set. So we do post quantization based on the calibration data set. So that's what pretty much is done. But the customers, if they want to do quantization aware training, they could potentially do that. But in our case, we do use the calibration data set and then number of samples, and we run it multiple times over the quantization. And then in the end, when we get the quantization results, we have an option to show the customers what is the accuracy loss that they got by going through our quantization mechanism. And we have run all the networks I showed through the quantization mechanism. And the error is pretty much within the 1% range is what we have seen on the networks we have run.
And you said you could use different quantization on a per channel or per layer basis, is that correct?
Per tensor, per channel, symmetric, asymmetric. As long as it's linear quantization, we'll support it.
Okay, so int 8 or int 16, or what data formats other than int 8?
Int 8 only.
Okay. Okay, so I guess I'm not understanding what you mean by per channel and if it's always int 8.
So basically every channel you could have a different quantization metric. Your scaling factor and your 0 point per channel can vary. So instead of right. So you're getting more accuracy by doing that as opposed to having one factor for all of the channels. So that's where accuracy.
Yes, sorry, go ahead.
That's how you can gain the accuracy back by having per channel.
All right, sure. So different optimization control parameters. Targets. Then in that quantization process, are you doing any pruning or sparsity measurements, optimizations?
We are looking at it right now. No, we are not doing any of the pruning or sparsity optimizations. It is something that needs to be looked at. The only thing we do take care of during our computation is the zero detect. When we see zeros, we do save power by not computing against it. But no, in the metrics we showed, we are not accounting for sparsity yet. But that's one of the optimizations potentially we can leverage in future, but not yet.
Sure. Okay, great. Let's see, we have a question on what would your initial target markets be for your SoC?
So because we are developing the edge SoC that is complete with the capability to support IP cameras or MIPI based cameras, and it's for the computer vision market, we should be able to target any of the edge markets like robotics or smart vision, surveillance, high-end security, etc. So those are the first key markets we are focusing on. But there are a lot of customers who are interested in the automotive side of things also based on the performance we are showcasing. So we are looking at few of those customers as well.
But for automotive, would you need to include any additional functional safety features? We had some discussion about this last week at the conference.
Right. So we are following all the processes and the development methodologies needed for certification. But we are not. We do plan to get the certification for the IP later on after we tape sometime next year. But the processes to make sure that we are not retrofitting after the matter of fact to get it compliant, those things we are already taking care of, both from hardware capability perspective, the methodology perspective, processes perspective. We have the right things that we are focused on, but we are not looking at certification anytime soon. Sometime next year is where we'll look at it.
Sure. Kelly, question on how do you handle any customized or new instructions that perhaps you didn't anticipate when you designed your core?
A very good question. So what we do is we will have a custom operator support. So what that is, in fact, so what we are planning on supporting, again, it's active development that's happening right now, is through the relay IR. What we can, so the customer can program through the relay what custom operator they want to program. And if it is capable of running on our MLA, when we go through the SDK, it'll target our MLA. If we cannot, it'll target the APU. But from that perspective, again, we are trying to make it as simple as possible from a customer perspective. Just code it in the relay using the relay ops, and that's all is needed. So it could be PyTorch, it could be TensorFlow. As long as they're able to code it using the relay ops, it should work. And where it gets targeted to will be a decision done internally.
Okay, got it. See, we have other questions from the audience. Well, the tops per watt that you assume the 16 nanometer design, that's not, that is the target, right?
Correct, 16 nanometer is the target.
Right. And I think a lot of the attendees are interested in hearing some hard numbers on the performance. Will you be able to discuss those more later on in the breakout? Or?
Definitely, we could look at some of the KPIs, or also please contact us offline. We'll be willing to share some of these KPIs with you. We have the data in-house, and we could always share it.
Have you looked at utilization? There's a question on efficiency. How well are networks mapping to your accelerator? Utilization are you seeing?
Yes, we do look at that as one of the factors, and it's all model dependent. It depends on, because ours is a 50 TOPS part, it all completely depends on how the model maps onto this thing, but we do look at utilization as one of the key metrics.
Okay, good. Let's see. Don't see any other questions from the audience. Well, let me ask you then also, since MLperv has been in the news a lot this week, would you be submitting to the MLperv scores?
Right now, we have looked at a subset of MLperv networks, and we have run them in-house, and we have KPIs for it. But once we have the silicon, we do plan to support MLperv and go through that process.
Okay, great. I'm not sure. The question here is, do you envision needing a separate SoC to run the apps? I mean, is this a standalone chip? Do you see this being a coprocessor?
It could be operated in both ways. It could be a standalone processor, or it could be a coprocessor too. So from that perspective, when we look at the IOs, we have PCIe, in which case you can connect to a host computer, and you could be an endpoint that's a coprocessor. That's one of the possibilities. But we also have heterogeneous compute on the SoC itself with APUs and the this thing, and we have APUs, our MLA and CV processor, and we have MIPI CSI too as interfaces or Ethernet. So you could run it as a standalone processor too. So you could run it for IP cameras, or you could run for MIPI CSI based cameras. You could be a coprocessor, or it could be a standalone processor. All the options are available from a customer perspective.
Okay, great. The question again on the on-chip memory. Somebody who is paying attention to the block diagram and remembered it shows 4 megabytes, but you said 20. So what's the discrepancy there?
So the 4 megabytes is the generic SRAM for the entire chip, but for the MLA itself, we have 20 megabytes built in it. Okay,
so you have local memory with your Mac units.
Right. So we want to make sure as it's a right partition between the local memory and the external memory. We didn't want to go too much into all on-chip memory or all off-chip memory. We struck a right balance based on our architectural analysis as to what is the right partitioning, so that we are able to hide the memory cycles behind the compute cycles and extract the best performance. And that's how we came up with it. And also from an SoC perspective, we want to avoid as much going to the off-chip memory. So we have some SRAM on the chip so that we can avoid going to the external memory if possible.
And you must have some memory allocated to the computer vision pipeline as well.
Right.
Yeah. Okay. 20 megabytes is the total then for everything. Okay. I don't see any more questions, and we are about at the end for this session. But you will be in the breakouts later, and people can ask more questions then.
Thanks a lot, Mike. Okay. Thanks a lot to all of you for attending. It really appreciate it.
Okay. Thank you very much, Kavitha. We'll talk to you later.
Sounds good.